Welcome to another read along with Dr. Powell in the book Discrete Perspectives in Mathematics. And we'll take a look at section 1.3. So functions can sometimes preserve structure. And we're going to be taking a look at that. What does that mean? What is it? What are some examples of structure? So for instance, if we're looking at integers, we think about addition among integers. If you add two integers together, you get another one. The idea of adding within that set and getting something in that set, that's a structure on the set. Addition itself is a function, actually. Think about it. Here's the domain, z cross z, so pairs of integers, and the codomain, integers. It's actually a function. It's a rule. All right, you could notate it like this if you wanted to. Think of the plus symbol as being like a function letter of 1, 6 is the input. You get out 7. That's kind of a funny notation. So we don't usually do that. We say like, so we might say 2 plus 3 is 5 instead. But it really is a function. We have a term here, binary operation associated with the set. So if we have, we take a pair of things and we output something else, we could think of that as a binary operation, like A star B, whatever that is. A closed binary operation is when you actually output something in the same set itself. You don't go out of S. Okay, so if it's a closed binary operation, we can sometimes call that operator. Okay, this whole idea, basically, we can interchangeably use the idea operator with operation. Okay, but in both cases, operator could apply to both cases. Okay, so we want to talk about when a function preserves an operation. What does that mean? It's kind of like a function, but wait a minute. An operation is a function itself, so it's like a function preserving a function, right? Okay, let's think about this a little bit. We'll build up these ideas a little bit. Let's suppose we have a function. Well, let's just start with a merge even, okay? Because every function is built off of a merge and a relabeling. So why don't we just do a merge first? So the outputs are, like just the chunks, all right? So we could think any merge function at all, you could do a little relabeling here, and that's fine, but you keep it as one of the things in the fiber chunk, but then you put a bar over it, and that still works. I mean, you just relabel it just with putting a bar. The merge function is perfectly fine, but that putting the bar means you're going to a partition, really. So basically you go from element of chunk to chunk itself, and that is a function. That is a merge function, perfectly acceptable. Okay, so that's what we're going to start with here and see what this means to preserve addition when we partition it up. In particular, we have these skip pattern merges that we introduced before. These actually preserve addition very well, and we'll talk about that a little bit. All right, in chunking this up and what that means. Okay, so well, first of all, we have a function. So the addition function right here from z cross z to z. So we take an ordered pair and we add them together and get something out. What we'd like to have is we'd like to have a corresponding thing happening with the image or the result of this function, but in its codomain, which is the partition P of the chunking. So within the chunks themselves, can we take a pair of chunks and add them together and get a new chunk? Yeah, like 1 bar plus 2 bar. Do we get a chunk 0 bar? And does that work well? Is that well defined, this process of this, as we go from this addition to here, is that preserved nicely? Okay. All right. So let's kind of take a look at how this is going to go. Um, so we have what we need for structure to be preserved is we need some kind of commutative diagram to work. Meaning that if we take the pair over here and we look at the corresponding chunks and we add among the chunks and we get a new chunk, it should be the same result as if we added over here before we apply the function. And then we apply the function, we get this chunk over here. This should work both ways. Basically what it means is if we add before the function or after the function, we should always get the same result. So we add before, we add after, we get the same thing. Using this notation for what the addition, structure, definition, whatever will be of the chunks together. And sometimes you can even write it like this, right? So kind of what you're doing is you're making a new operation among the chunks. This function really is applying to this whole thing. F of A plus B, you're going F of A, F of plus, F of B. All right. So that's what happens exactly when structure is preserved for an operation. Okay, preservation of a binary operation. All right. So, how do we see that this will work in this case with our chunking into 0 bar, 1 bar, and 2 bar in the skip pattern of multiples of 3? All right. So, well, we'll just kind of go through and see what we get when we go one way or another. So, well, just with some examples, first of all, right? Okay. So if we do 1, 2, and we add them together, 1 plus 2, that'll be 3, and we put it over, it'll be 3 bar, which will be 0 bar, right? Well, if we go on this way route, we go 1, 2, we go, well, 1, 2, we'll go to 1 bar, 2 bar. So that's what this notation really means. It means just basically say take 1 and put out 1 bar, take 2, put out 2 bar. That's what the cross means. We're just applying the function f component wise for each component. So in this component and then that component. Okay, so what we want to do is we want to be able to add 1 and 2 together, 1 and 2 bar. And what should it be if structure is preserved? It should be 0 bar. It should be 0 bar if this is going to work. At least that's how we should define this addition. Because if we go this way, we get 0 bar. So if we go that way, if this structure is preserved nice, it's addition structure, we should be able to define this as 0 bar and have a very nice addition there. Okay. So, sure, well, we can define it that way, but the problem is if we keep on, in fact, notice I kind of gave a general sense for how we should define it. Let's just define this as this by pulling the bar over the operation. Okay, well, the bar is kind of like the function anyway, the merge function. And this is like putting the operation before the merging or after the merging, right? So let's just define it as this as being what happens this way, adding before the merge. Let's just say that's what it is, but let's see if it works. And it might not always be well defined though. If we do that, we might run into some difficulties. What difficulties could we run into? Well, maybe what might happen is, well, let's see, there's different ways of representing 1 bar and 2 bar. For instance, you take 1 bar and 2 bar, you want to add them together, you want that to be well defined, but wait a minute, they didn't just come from 1 and 2, they also came from 4 and 5, because 4 is in the chunk of 1 bar and 5 is in the chunk of 2 bar. In this chunking process. So if we define it this way, 4, 5 goes here to 4 plus 5, 9 bar. Well, we better be sure that 9 bar is going to be the same as 0 bar. Okay, so we would need that to hold in that particular case. If you just have one instance of any of this failing, it won't work. We won't have a commutative diagram. So we need to be able to show this happens all the time, okay, for every single instance in every single case. All right. In order to know that, all right. So first of all, let's just kind of look down here and look at this next subsection. All right, so it's entitled, "Is our merge a good choice?" Okay, well, let's start with just merging two integers together. All right, and see, let's not kind of, so basically what we're going to do is let's assume that that we've only merged two things. You notice 0 bar and 1 bar and 2 bar, we've merged like a ton of things together, right? Maybe we've merged too much. So let's just be careful. Let's just kind of work backward or work from the go from the front and say, like, what happens if we just merge two things together? Okay, and what has to happen? All right. So what if um, we simply decided to merge 1 and 4 together and nothing else at the moment? Let's just merge 1 and 4, but know that we want addition to be preserved. How are the chunks going to change in that merge? Like, what else do we have to merge? What else do we have to chunk together instead of just 1 and 4, so that this addition preservation idea will work? Okay. And kind of what we're going to do is we're going to think, well, addition before has to be the same as addition afterwards, or they have to correspond. All right. So let's just think about addition sentences for a minute. Like, for instance, 3 is equal to -1 plus 4. Okay. So we know that 3 bar is equal to -1 plus, or is equal to -1 plus 4 bar, right? Because 3 is the same as -1 plus 4. All right, that's great. So let's think about this. 3 is equal to that. Well, basically, since things has to be done after, should be the same after, should work after as before, then what's happening is we should be able to make replacements. So think about 4 is going to be in the same chunk as 1. So if we replace 4 with 1, right? So anytime we replace anything in the same chunk, we're going to get, then what we get out here supposed to have the same result or image via the function f, the merging function. Well, it does. We're in the skip pattern. 0 is in the same chunk as 3. So we were successful in that replacement. So that means that, well, I guess that's if we're assuming that the chunk that we wanted the skip pattern merge. So basically what we've actually shown is that 3 has to be merged to 0. So if 1 is merged to 4, 0 has to be merged to 3, because if we replace 4 with 1, right, both results should go to the same place in the end. So by replacing 4 with 1, we should, we look at the results, these should also merge. 3 and 0 should also merge together. Okay. Well, if we keep on looking at different addition sentences, notice 0 is replaceable with 3 now. So think 0 is equal to 0 plus 0. So you should be able to replace anything here. So 3 is equal to 0 plus 3, 6 is equal to 3 plus 3. So we can replace 0, 3, and 6 can all replace each other. So that means that the chunk that includes 0 should also include 3 and also include 6. And if we keep going, include 9 and everything, because we can have 0 plus 0 plus 0. We can replace all those with 3s, and so forth. We get all the positive multiples. But also keep in mind that 0 is equal to 3 plus 3 bar, or -3, right? And if we replace 3 with 0, okay, then we actually got -3, which means that -3 and 0, they also should be in the same chunk, which means you actually get all positive negative multiples of 3. So basically what we've shown is that all multiples of, so even if we just merge 1 and 4 together, actually what we're getting is all multiples of 3 have to be in the same chunk. Well, if you have that, you actually, by working through some things, actually see that everything that's 1 more than multiple of 3 also has to be the same chunk. Well, in its own distinct chunk, which is different than the other one, maybe, perhaps. And similar with 2 more than a multiple of 3. Problem, though. do we know, is that enough merging? Is there any more merging that needs to be done in order to ensure that this works? I mean, we kind of have this kind of intuitive sense for this is kind of what's going to happen, but does it keep going? So that's where subsection 1.3.3 comes into play. So in this subsection, we actually work through proof of that by making things a little bit more general and looking at terms and so forth and building that out. So I'll let you look at that in there. And one last thing to conclude this section 1.3.4, compact set builder notation. All right. So sometimes we can think of a 3Z itself as a set. What set is it? It's 3 times everything in Z. So multiples of 3. Notice it can kind of be thought of directly from set builder notation, 3n, where n is element of Z. We just replace the n with a Z and you have this. So I call this compact set builder notation. It doesn't always work. From all set builders notation, there's some exercises which kind of explore that idea a little bit. But still it works in this case. 3Z plus 1, what does that represent? It represents everything that's 1 more than a multiple of 3. And 3Z plus 2 represents everything that's 2 more than a multiple of 3. And you can represent this by a 1 bar, a 0 bar in this case, or 1 bar, 2 bar, and a 0 bar. All right, so that concludes section 1.3. Thank you so much for watching.